Hi, this week we're going to talk about systems of equations, and we're going to start this week by talking about the simplest type of systems of equations, systems of linear equations. Now you'll be studying these a lot more in your linear algebra course when you get to that. Now what is a system of linear equations? Well, it's a set of equations that are all linear. That means your variables don't have an exponent other than, of course, the implied exponent of 1. So you don't have anything fancy like square roots or logarithms or anything. Just nice linear expressions for every single term. Now, for a system of linear equations, if we want to find a solution, well, it needs to be a choice of values for x and y that satisfy all of the equations in the system. So for instance, if I try to plug just some arbitrary made-up numbers like x equals 1 and y equals 2 into this system of equations here, well, what would I find? Well, for the first equation on the left-hand side, I'd get 3 plus 14. Well, that's certainly not 6. Well, I could try and maybe say, okay, that's not working. How about x equals 2, y equals 0? Because then I get, for the first equation, 3 times 2 is 6. Then plus 7 times 0 is 6. Okay, that's good for the first equation. But when I try to plug into the second equation, I get negative 4 plus 0. That's certainly not negative 1. So how do we solve? Well, we're going to play one equation off the other. And since we're going to be moving back and forth between the two equations, I'm going to start off by labeling my two equations, 1 and 2. And I'll refer to them in my solution. So the first thing you want to do is isolate one of the variables in one of your equations. So I'm going to start off by, let's say, isolating x in the first equation. Well, what do I get from that? I'll get 3x is equal to negative 7y plus 6, dividing both sides by 3. I get this expression here. Now I'm going to come back to this equation later on, so I'm going to give it its own number. It's equation 3 now. Now from here, I've found an expression for x that involves only y. So I'm going to replace or substitute x in equation 2, and the only equation I haven't touched yet, with negative 7/3 y plus 2. So what do I get? I get that negative 2 times negative 7/3 y plus 2 plus 5y is equal to negative 1. And notice that's an equation that has only y in it right now. So I should be able to find that value of y. Now I'll distribute in the negative 2 there. We'll get 14 over 3y minus 4 plus 5y is equal to negative 1. Now combining my like terms there, we'll get all the y's on the left. So we've got 14/3 plus 15/3 would give me 29/3 y. And on the right-hand side, looks like we would get 3. So when I multiply both sides by 3/29 to isolate y, I'd get y equals 9 over 29. Okay? Maybe not your favorite number, but it's exactly the number we need, that one value. Now, I've found the value of y. All I need to do is find the x that goes along with it. Now, if I look back at all my equations here, I could, of course, plug y equals 9 over 29 into the first one and isolate x. I could also, alternatively, plug it into the second one and isolate x. But the easiest one would be to actually plug it into 3, which is why we gave it its own special number. It's already of the form x equals this. It's set up to take a y value and instantly compute the x value for you. Okay, so let's continue along. We're going to substitute y equals 9 over 29 into equation 3. So we get x is equal to negative 7/3 times 9 over 29 plus 2. Now, I certainly do not want these numbers to get out of control, so let's divide out that common factor of 3 that we see in the top and bottom there, and we get negative 21 over 29. Let's write 2 as a certain number of 29ths. It's, I guess, 58 over 29. Add those up, and we get 37 over 29 as our x value. So that's great. We found the solution, probably not one we would have guessed, for this system of equations. The only choices of x and y that satisfy both equations at the same time are x equals 37 over 29 and y equals 9 over 29. Okay. It's a good example, shows the main steps, has some fractional arithmetic. Sometimes it can't be avoided. Let's take a look at some other examples here of what else can happen. I guess before we go on, let's just quickly review that key tactic. So your key idea is choose one of the equations. It's your choice. And once you've made that choice, you can choose either variable, or whichever variable you want in that equation, and isolate it. So you have lots of choices there. Some choices are better than others. Anything will work, but some are easier than others. So think a little bit about that. Isolate that variable in the equation of your choice, and then substitute in the expression on the other side of your isolated variable into the equation you haven't used yet. And you can use that to find one of your variable values. From there, you can plug in that variable value into your equation 3. Hopefully you set that up, and you'll be able to find the value of the other variable if we have just two variables here. So, let's take a look at this system of equations here. Number 1. I've got lots of choices. I can take my equation 1, and I could isolate x or y. If I isolate x, I'll end up with some quarters. If I isolate y, I'll end up with some thirds. How about equation 2? If I isolate x, well, I wouldn't get any fractions at all. If I divide everything there by negative 2, I'd have no fractions. If I decide to isolate y, divide everything by 10, I would get fractions. I'd get some fifths, it looks like. So I think the best choice, if we want to avoid some fractions, is to isolate x in equation 2. Of course, any choice you make will work. It's just how easy or difficult it is. So, we'll isolate that x as we said we were going to. I'll divide everything by negative 2. And notice there are no fractions that are created. This is the only choice, out of the 4 that would not create any fractions. So let's call that equation 3. I'm going to use that later on at the end to find the value of x. But for now, let's find the value of y. We used equation 2 already, so let's use the equation we haven't touched yet, equation 1. So we're going to replace x in equation 1 with 5y minus 3. So what do we get? We get 4 times 5y minus 3. The brackets are very important there because we'll definitely need to distribute. Minus 3y is equal to 0. I distribute. We collect our like terms. And we divide both sides by 17. And so now we found the y value. All we have to do is find the x that goes with it. Well, I'll substitute that y value into an equation that is perfectly set up to calculate the x value for us. That's equation 3. So we get, x is equal to 5 times 12 over 17 minus 3. Well, there we get 60 over 17, and minus, well, 3 times 17 would be 51. And we get 9 over 17. Okay. So we get our solution. And we have to report on both values. We can't just know one of the values of the variable. oh, sorry, x is 9 over 17. We need to state the values of all variables there. Because the solution to a system of equations is an assignment of values to all the variables there. Let's try another example here. All right, so here again, we'll label our equations. If I look at equation 1, if I isolate x, everything would be integer. If I isolate y, it looks like I would get some thirds. In equation 2, if I isolate x, well, 7 divided by 3, that'll be thirds again. And if we isolate y, we'll get some ninths. So it sounds like the best one is to isolate x in equation 1. So we'll get the 6y over on the other side and divide everything by -2. We'll call that equation 3. And then we'll replace x in equation 3, in equation, which one haven't we used? Number 2, with 3y plus 2. So we get 3 times 3y plus 2 minus 9y is equal to 7. Oh, this is not good. We get 9y minus 9y is no y's at all. On the left-hand side we get 6. The right-hand side we get 7. This is a disaster, folks. This means I'm completely out of a job. Alright, we have an inherent contradiction. I hope 6 is not equal to 7. Okay? If it is, I'd love to give you $6 and get 7 in return. So what's gone on here? Well, we made a fundamental assumption when we start to solve this equation. The assumption is that a solution actually exists. So based on that assumption that there are x and y values that will satisfy this equation, or this system of equations, we went and proceeded. But we certainly ended up with a contradiction. So our big problem was that we assumed the solution exists. That means this system of linear equations doesn't have any solution. Okay? Maybe there's another way, if you look at it, you could find that out for yourself. But I'll leave that to you to think about. Now, when you go to your linear algebra class, you will learn that every system of linear equations either has no solutions, like the example we just saw, has a unique solution, like the very first example we did, or has infinitely many solutions. And we didn't really talk about those, but you'll go into much greater detail in your linear algebra course. Now this week we'll talk more about systems of equations, and we'll talk about nonlinear equations, and we'll also do some word problems that use systems of linear equations. Thank you.